Okay, I think most people are here now, so I'll slowly get started. Last week we talked about several things. We talked about the t-test, chi-square test, Anova, and simple linear regression. And the fifth subject was multiple testing correction, which is something you do over the rest of your analysis. But let's have a very brief recap of the methods we've had so far. So, anyone know what the t-test is for? Yes, comparison of group means. How about the chi-square test? Yeah?
Compare observations with expected
Yeah, observed to expected
frequencies.
frequencies, exactly. Okay, and for Anova, for some reason I already wrote it down. And what was simple linear regression?
If we expect a linear relationship between the response variable and the explanatory variable.
Yeah, so if we expect a linear relationship between the response and the explanatory variable. And remember that linear means nothing more than intercept and slope. And how the actual relationship looks, so logarithmic or a line, that doesn't really matter. Okay, yeah, so today we're going to expand on what we've had so far with regards to linear regression. So I'll give a very brief recap of simple linear regression, and then we're going to the actual interesting part, which is multiple linear regression. Now, most of the time, you're not interested in a simple linear regression. For most research, you would do some form of multiple linear regression. And the reason for that is, let's say you're in clinical science and you want to show that one thing is linear related to another thing. And then a reviewer says, well, does that depend on age? Does that depend on the sex of the patient? So with multiple linear regression, you can just add those as variables to your model, and then you can account for their effects. So that's why in most scenarios you would have more than one explanatory variable. It isn't very complicated in R to add explanatory variables. You just add a plus sign or a multiplication sign depending on whether you want interaction. But the difficult thing is, once there's multiple linear regression, once you have more than one explanatory effect, then suddenly there's a whole range of phenomena that we have to take into account. So that's what we're going to discuss today. So in the first lecture, I will explain what Ancova is, which is a special case of multiple linear regression, and what interaction is. And then in the second lecture, I will talk about model selection, which is, I think, the most not complicated, but the subject of this course for which you have to know the most things. So there's a lot of different steps involved in model selection, a lot of things you have to think about. So today is going to be very heavy with regards to the amount of information, but that is on purpose because it's Monday, which is everybody's favorite day. No, I mean to say that we're at the beginning of the week, so you have a long time to let it all sink in, and in all of the exercises you can apply these things that we're going to see today. So, first of all, simple linear regression isn't very difficult. It's just you have a model where you have the intercept and the slope as a relationship between the response and the explanatory variable. And the slope is just the amount which the response variable increases when the explanatory variable increases by 1. Now, when we consider actual interesting research questions, then usually one line doesn't really capture the relationship. Even if there is a true relationship, there's always a lot of different things that can cause small random deviations between subjects. So it's not just a line, but there's also residuals, right? Because there could be small differences in exposure to sunlight, or genetic differences, or minuscule differences in temperature across your experiment, and humidity, and the soil could be slightly different over here than over there, etc. And you can think of a million things that will, to some extent, affect the outcome. Now, because of that, your model is always wrong. It always, captures the relationship more or less, but it doesn't capture the exact behavior of your data, because there's always some noise left. And in our data, we call that the residuals, the remainders. Now, because of that, we have to check whether this noise, these residuals, these remainders, whether they behave as we would expect if there is a true linear relationship in the population. And that's why we make certain assumptions. And if those assumptions are reasonable, then our model is reasonable. So can anyone help me remember what the assumptions were? Yeah?
Linearity,
Yes?
constant variance, residuals.
Yeah, so linearity, constant variance across the explanatory variables, so that means the variance over here should be more or less the same as over here. Anything else? Yeah, normality of the residuals. So we expect that if we take all these positive and negative differences and we plot a density plot or a histogram, that it should be more or less normally distributed. And the last one, and the most important one, I'll give you a hint, we cannot check it through visual diagnostics. Exactly, independence. That's crucial for valid inference. So, let's see. Oh yeah, it fits. So we expect that the observations are independent of each other. We also assume that the error is approximately normally distributed. Of course, we assume an exact normal distribution, but the method still works fine if it's only approximately normal. We assume that the variance of the error is more or less constant as we travel across the regression line. And finally, we assume that the relationship is actually linear. And the mathematical way of stating that is saying that the error is independent of x. Because if the error, the size of the residuals, changes as we go along the regression line, over here it's higher, over here it's lower, over here it's higher again, that means there's something left that's not linear. Now, to check this and to check for outliers, we use diagnostics. Now, the way to do that is to use the function LM in R, linear model. Then the first thing that you put into this function is the outcome, the response variable. And the second thing is the predictor, or the explanatory variable. So for example, with the iris dataset, which is a dataset of 3 types of iris flowers, and they measured the physical dimensions of the sepals and the petals, so the length and the width. Now, for example, we could regress the length of the sepals as a function of the length of the petals and see, is there a linear relationship between the two. The reason I'm giving this particular example is because, of course, there doesn't have to be a causal relationship between response and explanatory variable. It could just be that, you know, when one increases, then on average the other increases. That's a linear relationship. It doesn't have to mean that one is causing the other to increase. Okay, then we have the diagnostic plots. Usually I prefer the one from the package car, but in principle you could just say plot model, which will give you 4 plots. And usually I add this little part at the beginning, which says I want to plot in a 2x2 grid. The reason for that being that if you look at any of these in isolation, it is really hard to say what is going on if you see a deviation that's problematic. So for example, here we say, oh, okay, it looks a bit like this. But you know, when we look at scale location plot, we don't see any kind of problematic increase over the values of x, which means that this is just an artifact of the sample size. Now this one we used for outliers, and this one to check for normality. Okay, then once you conclude that there aren't any problems, then the next thing that you can do is you can print the summary of the model, which will give you all the coefficients that have been estimated, plus measures of their uncertainty, so their standard error. Now, if you remember, if you have an estimate and you want to know, is this significant, like is there a significant linear relationship, is the same as asking, is the slope significantly non-zero? You know, could be positive, could be negative. That means that we can do a one sample t-test with this. We can take the estimate and say, okay, the value under the null hypothesis is that the slope is 0, because then there is no linear relationship. So we take the estimate, we subtract 0, which doesn't do much. So and then we divide by the standard error. So simpler speaking, we just divide the estimate by the standard error, and that will give us a one sample t-test for the significance of the linear relationship. Now, this t-value, I already told you we're not going to look up tables because nobody does that in practice. but it will give you a p-value if you take the t-distribution and you take the surface area from this t-value onwards, and that p-value in this case happens to be less than 2 times 10 to the power of minus 16, or in other words, very small, which means that there is a significant linear relationship. Is that clear? Okay, one little side note. The fact that there is a significant linear relationship is not evidence that the relationship is linear, right? So your model could be wrong and the coefficient can still be significant, right? So if here's a parabolic relationship, like quadratic or logarithmic or sinusoidal, you could still have a significant estimate. This just means if we model this relationship as a linear relationship, then is that relationship significantly non-zero, right? So it's still important that you think about, do my assumptions make sense? And it's still important that you look at the diagnostic plots, because this p-value could be misleading. But in our case, you know, it's perfectly reasonable to assume that flowers with larger petals will have a linearly larger sepal. So that makes sense. And also in the diagnostic plots, we don't see anything that's worth our attention. So this is a valid, we can use this for valid inference. So in this case, I would say there is a significant linear relationship between the petal length and the sepal length. Okay, then I've removed some things over here. Let's go over this table, see if you can interpret this, because that will be almost exactly what you get on the exam. So the first one, a unit increase in petal length corresponds to how many millimeters longer sepal length? I should add on average. Yes?
0.40, 41.
Yeah. By the way, is this readable in the back? Okay, I see some not very convincing nodding, so I'll make it a little bit bigger. Yeah, 0.40. So, assuming this was measured in millimeters, then for every unit increase in petal length, we have a 0.4 increase in the average sepal length in millimeters. Yeah? Okay, second one. Theoretical flower that has petals of 0 millimeters. How large do we predict its sepals to be if the petals are 0 millimeters? Could you speak up a little bit?
4.3.
Yeah, 4.3. And why is that? Yeah, the other way around, but that's correct. That's the intercept. So if you take a petal length of 0, then you just do 0 times 0.4, and what you're left with is only the intercept. So that means if I plot this on x against y, then where does it hit the y-axis? That happens to be at 4.3. So in other words, if the petal length is 0 millimeters, then we would expect the sepal length to be 4.3 millimeters. Yeah? Doesn't mean that that's a realistic estimate, you know, because usually we are a little bit skeptical about extrapolating beyond the range of your data. And there's no guarantee that the linear relationship holds at 0 millimeters petal length. But that's what the model says. Okay, if we use these two, so in other words, if we use this model, this linear relationship, how much of the variance in sepal length does that explain? Yeah?
76%.
Yeah. So that's the r squared. Yeah? 76%. In the output it says multiple r squared. That's because you can use this same measure when you do multiple linear regression. Yeah? But if you do single linear regression, you don't have to remember this, but then it is just r squared. Okay, finally, the estimates for 1 and 2 are significant or insignificant. Little louder, please. Significant, yeah. Why? Yeah, exactly. So for any reasonable choice of alpha, it would probably be, you know, less than it, because this is 2 to the power of 2 times 10 to the power of minus 16. That's a lot of zeros before you see a number. So this is very, very significant. Yeah, doesn't mean it's very, very important, but it is most definitely non-zero. Okay, yeah, so it's just printed in the slide if you want to have a look, but I'll skip this one. Then we can go to multiple linear regression. Now, multiple linear regression just means that you have more slopes. There's still one intercept because that's the starting point for the outcome. But now we say, okay, there is a linear increase with one variable and simultaneously a linear increase with another variable. So that forms a plane of possible values. And then if you know both of the explanatory variables, you can predict the response variable. So what I did here is I downloaded a very large data set on cardiovascular disease. And I used that data set to see if I can find a linear relationship between the systolic blood pressure, age, and body weight. And my idea was, okay, higher body weight individuals will on average have higher blood pressure, and older individuals will on average have higher blood pressure. And how much do either of these contribute to the average blood pressure? Now, this is how that works in R. You have your response variable, and now we have one explanatory variable plus a second explanatory variable. Yeah, so in this case it would be blood pressure tilde age plus body weight. And now we have two linear effects. This is what that looks like. You can have a three-dimensional plot. Well, it's still two-dimensional screen, but you get the idea. You can have a linear increase in systolic blood pressure with age, but anywhere on this line, we can still linearly go up in the other direction for the weight. Yeah, so that is how you can have linearity in more than one direction at the same time. Now, you have to take my word for it that you can also do this in 3, 4, 5, or 1,000 dimensions, because I cannot plot it. But the point being, it is linear so long as we have intercept plus slope times explanatory plus slope times explanatory, etc. Yeah? And also keep in mind that this relationship doesn't have to perfectly describe the systolic blood pressure, right? We have residuals, except now the residuals are the vertical distance to the plane and not to the line. Yeah, is that clear so far? Yeah.
If you have multiple variables, how can you still at some point determine if it's still linear?
That's a good question. So he asked, I don't know if it was audible, if you have multiple explanatory variables, how can you still determine whether the relationship is linear? That is really hard. And that is why we use the diagnostic plots, because the residuals versus fitted plot, still, if our assumptions hold, then there should be no relationship in the residuals versus fitted plot left. And if that's the case, then you can assume that linearity was reasonable. Yeah? Okay, now this is what the residuals look like. It's still just the vertical distance to the model, but now the model exists in more than one dimension. So yeah, it's a bit trickier to see, you know, is this normally distributed or is this heterogeneous? Is there constant variance across this plane? So yeah, and you can imagine if we add more variables, it becomes almost impossible to see this. Yeah, so it was a good question. That's why we use the diagnostic plots, because they look more or less the same as, oh, I was kind of expecting diagnostic plots to appear. They will appear later. But it looks more or less the same as with simple linear regression. Okay, then we have to discuss one more subject before we can get to Ancova, and that's dummy variable. Anyone know what it is? Also called an indicator. Okay, that's okay. It just means you have a variable which can only take on one of two values, 0 and 1. And it's a trick for us to incorporate categorical variables in linear regression. Because remember, linear doesn't mean line, it means intercept plus slope times explanatory. Now, if I want to have a categorical effect, what I can do is I can make that explanatory variable a variable that only takes on a 0 for one class and a 1 for the other class. And now, this is a linear model, but I have a categorical variable, namely, are you male, yes or no? Yeah, and yes or no is just 0 and 1. If I multiply it by 0, then it's just the intercept. If I multiply it by 1, then I will add a constant. Okay, this is what that looks like. And this is what we call Ancova, analysis of covariance. Because it's like Anova, we're comparing means, but now we are comparing how they vary across another explanatory variable. Yeah, so here we have the model. I don't know if this is readable, so make it a little bit bigger. It says the intercept is 0.3. Well, where is that? That's over here. Yeah? Then it says the slope of x1 is 0.8. So that means for every unit increase in x1, I expect to go up by 0.8. And then it says for x2, which is our dummy variable, you add a constant of 0.7. So that means if I am male, I add another 0.7 to this, and then the slope is still the same, right? So slope is still 0.8. Yeah? Okay, oh, there's a question.
Is the second x always the categorical?
Sorry?
Is the x2 always the categorical?
No, you can flip it around.
Oh.
Yeah, that's arbitrary. So he asked, is the second variable, so this x1, x2, is that always the categorical one? But no, that you can do it in any order. Okay, how many dummy variables would I need to have 3 groups? So now we have 2 groups. What would I need for 3 groups? How many dummy variables do we have right now? 1. And we have 2 groups. So how many dummy variables do I need for 3 groups? 2, yeah. Because all I need to do is I need to estimate 1 more offset, right? And now we have 1, 2, 3 different possible lines that are explained by this relationship. So let me go over that real quick. We still have an intercept of 0.3. Yeah, that's over here. Then it says, okay, the slope of x1, it's a little bit small, but this says x1 is 0.9. So that means if we go all the way 1 unit increase in x1, then we should be 0.9 higher. And then it says, if you are group x2, you add 0.7. If you are group x3, then you add 1.1. So that's over here. And if you're not group x2 and you're not group x3, then you must be group x1. So you need the number of groups k minus 1 dummy variables. Because if you're not in all of the other groups, then you must be the remaining group. Okay. Yeah, why is it called Ancova? Because it has a relationship to Anova. Anova is where you just compare sample means, so your whole model is just a bunch of intercepts or only dummy variables. And in Ancova, we estimate how these groups differ across another explanatory variable. Now, if you look at this, this is the same data plotted if I would analyze it Anova-wise or Ancova-wise. And you can see that Ancova much better extracts the relationship between these groups, right? The difference between these groups, I should say. So over here with Anova, we see that, okay, if we take the average across all of our x1 observations, all of the explanatory variables continuous, then, yeah, the difference is really unclear. This one is a bit lower, but, yeah, okay, are these different? I don't know. There's a really large overlap. But if I plot it like this, then you will see, if you produce a summary of this, that there's a very significant, a clear difference between this group, and that group. Yeah? So it's a more powerful approach. Okay, how do you do this in R? Same way we did the multiple linear regression. So we have Ancova is a linear model, which is the outcome, then a tilde, which is the wavy sign, and then, yeah, I've written continuous variable plus grouping variable, but you could do grouping variable plus continuous variable, doesn't matter, just have explanatory 1 plus explanatory 2 plus explanatory 3, doesn't matter if they're continuous or categorical. Yeah? Okay, one important thing to note is that R will automatically choose a reference group. So that means, remember the whole story about how many dummy variables we need. There will be one remaining group that's just equal to the intercept plus slope, right? R will choose which one that is, and it has a very complicated algorithm for doing it, which is called the alphabet. So it will just look at which variable is the closest to A, and which name, and that will be the reference group. So keep in mind, that's not always what you want, but it's very simple to change with the function relevel. Okay, so let's say that that's the case. Then let's say we create a vector of 3 different levels, and then we see what R does under the hood. So here we have one categorical variable with 3 different levels, and then we have 2 different indicator variables or dummy variables because this one says, okay, observation 3 and 4, they're equal to 1 in the dummy variable for group 2, right? Because that adds a constant over here. Everywhere else it adds 0 times that constant, which is the same as saying don't add it. Group 3, okay, apparently observation 5 and 6 are in group 3 because they have a 1 over here and all the other ones have a 0 over here. So what happened to group 1? You have group 2 and group 3. What happened to 1? Sorry? Yeah, it's the reference group. So it's just equal to the intercept, yeah? Plus 0 times group 2 plus 0 times group 3. Okay, yeah, this is called the reference group. If you don't belong to either of the other ones, you must be the remaining one. So you don't need 3 variables, and in the second lecture we'll see that you can't even add a third variable for it, because that is called collinear. Okay, sometimes you don't want the reference group to be the reference group. You want another of the categories to be the reference, right? Let's say that you have named your treatments A, B, C, and control. Then R will think, well, okay, A is closest to A, so that's the reference group. If you don't want that, then you can use this very useful function called relevel to specify which category you want to be the reference. So here I've shown how to do that. This is just a function for creating a vector, but this could be any vector, any categorical variable. Then I say relevel, then the name of this variable, and then the name of the group I want to be the reference. Now, if I do it again, I again create a, this is called a design matrix, but it just means create the dummy variables for this. And you see now we have a variable for group 1 and group 3. And then observation 1 and 2 have a 1 for this indicator variable, or this dummy variable, and all the other ones have 0. So that means this is group 1, number 1 and number 2. There is no group 2, but there is a group 3 that says, okay, if you're observation 5 or 6, there's a 1 over here, and the other ones are 0. Now, group 2 is just don't add this constant, don't add this constant, because it's just equal to the rest of the relationship, which is the intercept. Yeah? Okay, let's go back to the iris example, and then we're going to compare the simple linear model to the Ancova model, so a multiple linear regression. So this is how you do the first one, sepal length as a function of petal length, and here's how you do the Ancova version, sepal length as a function of petal length and species. Okay, so let's look at the diagnostic plots. Here we saw, a little bit of a bump, not problematic I would say, but let's just show that this model is in fact better. And here we see, a little bit of excess in the tail. And if we plot the Ancova, we see that it's completely flat. Yeah, this doesn't happen often, but this is very nice looking. So this is one way to determine which model is more appropriate, by seeing, okay, the diagnostic plots for this model show much less problems, so perhaps it is more correct. Yeah, here's without an effect for species, and here's with an effect for species. You see that the QQ plot is now almost exactly over the dotted line, and you see that the residuals versus fitted plot shows no relationship left at all. Okay, so let's produce a summary. This one takes a little bit more time to interpret, but it works the same way. So let's go over it just like we did with the first one. We have an intercept, we have an effect for petal length, effect for versicolor, and effect for virginica. Okay, so the reference group in this case is setosa, that's the remaining one. And then the first question, iris versicolor has how many millimeters smaller sepals than iris setosa on average? Is this readable? So-so? Okay. So versicolor, how much smaller are its sepals than setosa? Setosa is the reference group. Yeah? Yeah, minus 1.6. So that means 1.6 millimeters smaller than iris setosa. So how can you see that? There are two dummy variables, species versicolor and species virginica, and they are compared to the reference group. Now, the reference group is the one we don't see, so that must be setosa then. So that means that it has estimated the dummy variable equal to 1.6, negative 1.6 for versicolor. So that means that the line for Versicolor should be 1.6 lower than that of setosa, or in other words, anywhere across the line for petal length, the sepal length of setosa should be 1.6 smaller. Okay, how about Virginica? Yeah, 2.1 smaller than setosa, because again, this is compared to the reference group. So this one starts out 2.1 lower than this one. Yeah? So this is the actual starting point, right? So if you are a setosa flower and you have petals that are 0 long, then the width of your sepals is estimated to be 3.6 millimeters. Okay, how much variance does this model explain in sepal length? Yeah, so yeah, this is, if you round it, 83.7%. Yeah, that's just, again, R squared. Works the same for multiple linear regression, works the same for Ancova. Okay, last one. Yeah, are these estimates significant or not? Yeah, they're significant for any reasonable choice of alpha. These are all numbers of 10 to the power of minus something. If you do 10 to the power minus 10, that's a 0, and then 9 zeros after the decimal separator, and then your first number. So yeah, this is definitely significant. Okay. Yeah, so here are the numbers if you want to have a look after the lecture. Oh yeah, here's the example with re-level. Yeah, so what if I don't want setosa to be the reference group, I want something else to be the reference group. Then I say, okay, from the dataset iris, take the species variable and then apply the function re-level. This means overwrite or assign. Then re-level iris species again and make the reference group Versicolor. Now, then I just run my model again and I run my summary again, and now suddenly we have a dummy variable for setosa and for Virginica, because the intercept shows, yeah, intercept is now the reference group Versicolor. So that means that the starting point is the sepal length of a versicolor flower with a petal length of 0. And then, yeah, you can interpret it the same as we did the last one, except now we are comparing everything to this new reference group. So now we can compare setosa to versicolor. We could already do that because it was the reference group setosa and then against versicolor. So this minus 1.6 is now a plus 1.6, yeah, because we're looking at the other reference group. But now we can do something new. Now we can compare versicolor to Virginica. And we couldn't do that in the previous model because neither of them are the reference group. So that's how we can do Anova-like comparisons with a linear model. Okay, yeah, small side note, it doesn't matter for this example because the p-values are extremely small, but if your model has many p-values, then you should have a look at which ones do I need for my research question and count them and then apply some form of multiple testing correction. Okay, the last thing before we're going to have a break is interaction. We've already talked about this briefly in Anova, but it starts to become more important in Ancova and in multiple linear regression. So interaction just means that the effect of one explanatory variable depends on another explanatory variable. So a very simple example, yeah, taking the pill, the effect on ischemic stroke incidence. It depends on smoking behavior. So yeah, what does that mean? If you take the contraceptive pill with less than 50 microgram of estrogen, that doesn't pose much risk. But if you also smoke, then the risk of ischemic stroke is increased far more than only attributed to smoking. So that means that they interact. There's a synergy between them. Okay, so yeah, quick check. What is the response variable in this scenario? Yeah, stroke incidence, which, by the way, is something we cannot model yet because it's not normally distributed, but that we'll get to tomorrow. What are the explanatory variables? Yeah, smoking and taking the pill. So smoking, yes or no, or maybe in the amount that you take, and taking the pill, yes or no. And which two variables interact? Yeah, the same too. So the two explanatory variables are set to interact because the effect of one depends on the other. Yeah?
Do you need to be sure about this interaction before you do this, or could you?
Ideally, yeah, but we will talk about that in the second lecture. So she asked, do you need to know whether you want an interaction before you start modeling, or can you find it out afterwards? That's a bit difficult to answer. Ideally, you would want to know it beforehand, but the reason for that we will explain in the second lecture on model selection. Okay, yeah, they're written down here if you want to have a look. Okay, what does interaction look like? Here's a simple example. This is a standard dataset in R called tooth growth, and it's an experiment performed on guinea pigs where they give them different amounts of vitamin C. But it's also administered in two different ways. One is as orange juice, because that also contains other stabilizing elements, and one is just as a powder, so pure vitamin C powder. Yeah, so that one, it's called VC for vitamin C, which is the powder, and OJ for orange juice. Now, what's going on here? We can see that there is a certain difference in the effectiveness of vitamin C powder and orange juice, right? And we can, it kind of makes sense because orange juice has other stabilizing elements in it, or yeah, whatever you call it, substances. But if I increase the dosage, you can see that the difference between orange juice and vitamin C diminishes. So in other words, the difference between supplementation method depends on the dosage. And you can also flip that around. This reasoning works in both directions. The effect of concentration is different for these two. This one plateaus much earlier than the red group. Yeah, so the effect of one depends on another. Let's see. Oh yeah, how to do it? It's quite simple. Instead of using a plus sign, use a multiplication sign in your model. So here we have the length of the teeth is a function of the supplementation type and the dosage, and we want them to have an interaction. That's what you do with the multiplication sign. Yeah, another way to do that is to say I want an effect of the supplementation type, I want an effect of the dose, and I want an effect of their combination, which you do with a colon. Yeah, which of these to use doesn't matter if you only have two explanatory variables, but if you have many, we will see that it's maybe better to use this one. Okay, what does the output look like? That's why this one is a bit easier to understand, the lower one, because these are exactly the variables that we're going to see in the output. Namely, we have an intercept, we have an effect of supplementation type vitamin C powder, we have an effect of dosage, and we have an interaction between vitamin C as a supplementation type and the dosage. Okay, let's see if anyone is able to figure out how to interpret this. Starting with, if we have a theoretical dose of 0 milligrams, then the reference group, which is orange juice, would have an average tooth length of, yeah?
11.55.
Yeah. So, yeah, sorry if you can't quite read it, but this says 11.55. That's just the intercept, right? It's the reference group where all the other explanatory variables are 0. Okay, if you have a vitamin C as a supplementation type, does that result in smaller or larger teeth on average compared to the reference group? Smaller, yeah. How can you see that? Yeah, because we have a negative slope. Yeah, so this is a dummy variable. It only takes on values 0 or 1. So if you take vitamin C, it's equal to 1. If you take orange juice, equal to 0. This says if you take vitamin C, we start out 8.2 millimeters lower. Now, if you take orange juice, which is the reference group, then if I have a 1 millimeter increase in dose, how much longer do I expect the teeth to be? I'm going to let someone else answer now. It's okay, but... anyone else?
Is it 1.58?
How have you determined that?
From the second column for the intercept group? I'm not sure.
Oh, yeah, sorry. So these are columns. So this shows all the estimates. 1, 2, 3, 4. This shows their precision, yeah, or their imprecision. So let me repeat. If you are the reference group, what is the slope of dosage? Because that is really what this question asks. Yeah?
7.8.
Yeah, 7.8. That's just the normal slope for dose, right? But we have a second slope over here. So this is the part that we have to focus on, the interaction. So if you're the reference group, this works the same as any other kind of model. Just ignore the interaction and look at dose. If you're not the reference group, we have to look at two things at the same time. We have to look at the actual slope and at the difference from the slope if you are the other variable. Yeah, if you are the other group, I mean. So if you're vitamin C, then both this one is equal to yes, and we are using the dosage, which is equal to non-zero. So that means we also have to add this. So it means that the slope for dosage, if you are in group vitamin C, is 3.9 higher than 7.8. So in other words, the actual slope of vitamin C is 7.8 plus 3.9. Yeah, that's how to read a table like this. Yeah, so the 7.8 plus 3.9. Okay, how much variance does this model explain? I'm just priming you for the exam. Is it readable?
72%.
Yeah, and if we round, it would be 72, yeah, it would be 73.0%. Yeah? Okay, some of the other outputs. We have residual standard error. This one we're going to talk about in the second lecture. This has to do with overfitting and underfitting. Adjust R squared also. We are not going to talk about that until we know what model selection is, because then it becomes relevant. But this one we can talk about, the F statistic. Does anyone remember what an F test is?
Anova.
It's used in Anova, yes. What is it used for?
Variance.
Omnibus test, yeah. And what kind of test is that?
Comparing variance.
Yeah, a comparison of variances. This is an omnibus test which compares the variance in, group means we don't really have because we have dosage, which is continuous. So this is kind of hard to explain what exactly it is comparing, but you can think of it as the variance explained by the model divided by the variance that remains, the residual variance. And if that F statistic is non-zero, then apparently your model explained a non-zero amount of the variance. So this F statistic is like an omnibus test, seeing if there is any effect of all your explanatory variables with one test. So it's a very cheap test, because if this were the only thing you looked at, you wouldn't have to do multiple testing correction, and then you have a p-value. Does my model explain anything at all? Yeah? Not super important because we don't use it very often, but that's just so you know what this last part says. Then, how many observations did I have in this experiment? Anyone willing to take a stab at that?
Nine?
59. Any other guesses? 60? 58. Okay, let's start with one more question. How many variables would I need at least to estimate this model, to fit this model? How many effects were estimated? What about this one? It's number 4.
That's not a variable, or is it?
Yeah, but it is an effect. So what you do is you count the number of things that were estimated. So 4 parameters in this case, an intercept, 2 slopes, and a third slope for the interaction. And then you add 1. That is the minimum you need to perform this kind of research. You can fit this model with 4 observations, but you cannot compute any standard errors. They will all say not a number or infinite or something like that. So if you want to do this type of research as a pilot study, and you want to use as little observations as possible, okay, you have 4 parameters, you need 5 observations at the very least. How many observations did we have? Okay, there's 2 places where we see it, over here and over here. We see that there are 56 degrees of freedom, and in this line we see what they belong to, of the residuals. So there are 56 degrees of freedom left, we estimated 4 parameters, so we had 60 samples. Yeah? Yes.
And which one did you look at the F statistic?
Sorry?
The F statistic states 3 and 56.
Yes. Okay. Good question. Why does this F statistic say 2 different types of degrees of freedom? Anyone know what this 3 is?
This is group, right? That's this group.
Almost. Not groups, but... I mean, we have a continuous variable here, so effects. Yeah? So we have 3 effects of which we want to know are they significant, and we have 56 residual degrees of freedom. So this F statistic is on 3 and 56 degrees of freedom. Yeah, you don't have to know that for the exam, but that's how you can read this. Okay. Then, what if you cannot choose? What if from a biological point of view, you think, well, yeah, there could be interaction, but I don't know how strong it is. I don't know if there's significant interaction. Then there are different ways to do that. We're going to talk about that at length in the second lecture, but I'll give you one quick way to do it, which is like this. You fit both models. So here I have one model with interaction using the multiplication sign, and one model without interaction using the plus sign. And then I say AIC, Akaiki's information criterion, which we will discuss in the second lecture, but for now just remember lower is better. In this case, the Ancova model with interaction has a lower AIC, so that would be the better model according to AIC. You can also perform a test for this, and you know I am not really a fan of running tests for everything because of the multiple testing problem involved, but you can do it, and that function is, for reasons that are beyond me, called Anova. But it performs either an F-test or a likelihood ratio test, depending on what kind of models you compare. You don't have to remember that, by the way, but I just want to show you it compares both models by saying, does one explain significantly more variance than the other? And you get a p-value for it. So this is, it's 0.05. This would be a significant difference. Then, okay, which of these is better? Well, this one has lower RSS, residual sum of squares. And of course we want to have as little residual sum of squares left as possible, because then we have the most amount of variance explained. But at the same time, we don't want to use too many parameters, because having fewer degrees of freedom left will mean that we have worse parameter estimates. But in this case it says, okay, this difference is worth that extra parameter because the difference is significant. Yeah? So look at the direction of effect, which one has less variance, which one has less variance left, and then see, okay, is that a significant difference? But we'll talk about that in the second lecture. Okay, just a small side note. When you have something like dosage, we could already kind of see it here, but it's a bit hard to see because there's only 3 levels. But you can imagine if you take no vitamin C versus taking a little vitamin C, that's going to have a really big difference, right? And if you add twice as much vitamin C, okay, that might still have a difference. But there comes a point where adding more and more vitamin C to your diet is not going to give you linearly longer teeth, probably. So the way to model that properly would be with a logarithmic effect. Yeah, so I would think this is a better model, taking the logarithm of those and an interaction with supplementation type. Now we can compare this. So here I called it Ancova 2, and again I can do something like comparing the AIC. So here I have the AIC of the model taking supplementation type and dosage linearly, and here I have the model taking supplementation type and taking the logarithm of dosage. Now then we see that the AIC for the second model is lower, so that means Ancova 2, which is the one with the logarithmic effect, is better. Yeah? Okay, so in summary, Ancova without interaction is like saying there is a constant difference in group means along some continuous explanatory variable. And saying that you have an Ancova with interaction means that whatever the difference between these group means is, depends on where I am, depends on the other continuous explanatory variable. Whether you want to have an interaction or not depends on what makes more sense from the point of view of your experiment. Yeah, so if it's a biology experiment, think about the process and think about, does it make sense that this difference depends on this continuous variable? But if you're in doubt, you can use this AIC value, or you can use a test to decide for you. Okay, yeah, this is what we've had so far. And yeah, we can see that all of it can actually be done with a linear model, because the t-test in a linear model, how would we do that? Anyone know? Anyone have an idea?
What was the question?
How could I do a t-test with a linear model? Okay, so the answer is LM, response variable, and explanatory variable. But the explanatory variable is the grouping variable. So if I want to compare males and females in my t-test, then my explanatory variable is just a dummy variable that is equal to 0 for one of the two groups and equal to 1 for the other group. And yeah, simple linear regression. Okay, of course we can do that with linear regression. Multiple linear regression is when you want to have an effect of more than one explanatory variable in the outcome. Ancova is just a name. It's still multiple linear regression, but it refers to the case where we have both continuous and categorical explanatory variables. And finally, interaction is when the effect of one explanatory variable depends on the value of another explanatory variable. Yeah? So this is really important. And in the second lecture, we're going to talk about how you can choose which model is better. Oh yeah. Somewhere in the beginning, I showed a slide of Anova versus Ancova, and I said Ancova is more powerful. You can actually show this in numbers. You don't have to remember this part. This is just to show you that I am telling the truth. We have p-values here, right? Here we have an effect of length against supplementation type, which is just an Anova, right? We only have group means. And we compare it to the Ancova model. And we can actually see that the supplementation type here has a p-value of 6.0 times 10 to the power of minus 2, so 0.06, so just not significant with an alpha of 0.05. But if I also include the logarithmic effect of dose, or the linear effect of dose, then the p-value of supplementation type is much smaller. So that literally means my ability to demonstrate a difference in supplementation type is bigger when I also include the effect of dosage. Yeah, so it is literally more powerful. Okay, but yeah, that's just a small side note. This is the important part. Let's see the time. It's a little past 10. How long a break shall we do? Second lecture is quite long, it's about an hour. Although we could break it up with a small break in between. Shall we do 10 minutes? Is that enough?